Hi, in this video, we'll be delving into quantum physics. So, quantum physics first emerged when certain phenomena were observed at microscopic scale, right? Usually below the nanometer range, and physicists found that anomalies started to appear, right? And the physicists found that these phenomena did not obey the Newtonian laws of classical physics, and since they don't obey Newtonian laws, everything they knew of physics was not applicable at some atomic scales. So that's when the field of quantum physics was established, and some of these phenomena include the photoelectric effect and Young's double slit experiment. And in this video, we're going to be delving into the photoelectric effect, right? So one of the main theories of quantum physics is wave-particle duality, that light behaves both like a wave and it behaves like a particle. And the proof for light behaving like a particle comes from the photoelectric effect. So essentially, light comes in photons, right? And photons are quantized packets of energy. This is the definition for a photon. Okay, and what happens is, right, you know how electron shells are structured. You usually learn this in GCSE chemistry, right? So you have your nucleus, and then you have like certain electron shells, right? And let's say we have an electron over here. Now what happens is you have light coming in the form of photons. So let's say you have light rays coming, and they're coming in the form of photons, and what happens is the electron absorbs this photon. Let's say it absorbs a photon and it gets excited. That means it gains energy, and when it's excited, it moves up to a higher energy level. These electron shells all represent certain energy levels, right? And once the electron absorbs the energy from the photon, it's excited, moves up to a higher energy level, so it can move up to here. Let's say it moves here. And now what happens is now that the electron is excited, it then releases the energy, right? It releases the energy and emits it emits the energy basically, and it is de-excited sort of, and comes back down to its initial state, which was over here, right? And that's basically the concept of electrons getting excited and whatnot. Right, so how does the photoelectric effect prove that light behaves like a particle and not a wave? So what happens is based on observation, when this energy is emitted, right, the electron's excited, goes back to ground state and emits the energy, right? And when this energy is emitted, it's emitted instantaneously, right? And if it was a wave, it wouldn't be emitted instantaneously because it takes time for the energy to build up, right? So that's the first proof. So particles, there is instantaneous emission, and this is what is observed. Instantaneous emission. While in a wave, it would take time for energy to build up, right? Wave, right? It would take time. So that's the first proof, right? Instantaneous emission. Next, what happens is you find that when when these electrons absorb photons, they can only absorb photons with specific energy, right? Let's say the gap between this is, let's say this is I'm coming up with random values, right? So let's say this is 2 electron volts. Electron volts is a unit for energy, right? And let's say this is 6 eV and this is 9 electron volts. Okay, so in order to go from this energy level to this energy level, it must gain 4 electron volts. If it gains so if there's a photon coming in with 5 electron volts, right, then it would go to 7 electron volts, right? But there is no shell with 7 eV. There's only 6 electron volts. It can go to 9 electron volts. And since it's absorbing a 5 electron volts one, there will be no transition of the electron. It won't move up shells and it won't be excited. Or if it was, let's say it was 7 electron volts. Let's say there's a photon coming in, 7 electron volts. In this scenario, it will actually be excited because it'll go to the 9 electron volts one this time, right? Because 2 plus 7, 9. So it goes up to the 9 electron volts one, and then it's de-excited, emits the energy, and the energy emission is instantaneous because light behaves like a particle and not a wave, and in a wave it takes time for the energy to build up, right? So this is another thing, right? Particles only specific energies, right? While in a wave, what would happen is that you can have, what happens is over time, the energy of the wave builds up, right? So what would happen is like, let's say you have light coming in at photons coming in at like 5 electron volts. What would happen is over time the more energy would be added, and then it would reach 7 electron volts, right? And then it would actually end up being transitioned to the 9 electron volts one. So this is not true, right? And you don't find the energy building up. The fact that only specific energies can be absorbed shows that light behaves like a particle, okay? And then lastly, what you have is the relationship between intensity and energy, right? So generally in waves, what happens is if the intensity increases, the kinetic energy emitted increases, right? But this is not the case. What is observed is that as intensity increases, the number of photons emitted per second increases, not the intense. There's no effect on the kinetic energy of the photons emitted. There's only effect on the number of photons emitted, right? So that's the last point. Intensity no effect on KE, but on number of photons emitted per second, right?